Today we're gonna talk about pressure. No, not that feeling your mom gave your dad for not spending enough time with the kids. No, not that feeling you have when the exam is tomorrow and you haven't studied. I'm talking about pressure described in physics, like what you feel under deep water, or the air pressure you don't feel at sea level because we are evolved to be used to it. In the simplest term between solid objects, pressure is just the concentration of force. Similar to light, if it's focused to a point or a small area, the intensity increases, or for force, we say that the pressure increases. When it is spread over a large area, it becomes weaker and so lower pressure, which is why pressure is calculated as force per unit area. But what does the concentration of force, or aka pressure, even do? Well, force has the ability to move things. Therefore, if the pressure is high enough, it can then move the particles of an object away from each other, creating a dent or a crack. With this knowledge, we learn to create useful tools like knives with sharp edges to increase pressure so that it can cut through soft materials. On the other hand, we also make tanks with wide tracks and snowshoes that works the opposite so that it does not sink easily into soft ground or snow. But when it comes to pressure in fluids like gases and liquids, it works a little differently. Individual gas or liquid particles are constantly moving and colliding with itself and its surrounding, which collectively exert force that increases depending on how frequent the collision and how massive the particles. This pressure is more or less equal in all directions within an enclosed area. Since the mass of a particle simply depends on the type of fluid, let's talk more about how we can increase the frequency of the collision in an enclosed area in order to ultimately increase the pressure. The first way is by cramping particles together. In this example, the same amount of particles are placed in a smaller container. You can also add more particles to the same container before, and that will have the same effect. In this case, the tight space makes the particles collide with each other and the surrounding more frequently, and so it has a higher pressure. A good example is the atmospheric pressure, because when gravity pulls all the air particles down, the particles closest to the ground are compressed by the weight of all the other air particles above it, contributing to about 100 kilopascals of pressure, which is a lot. As you go higher in altitude, there's less weight in the total air particles above you to cramp the air around you, so you experience less pressure. In fact, the oxygen molecules are so far apart at higher altitudes that you may find it even hard to breathe. The second way of increasing pressure is to make the molecules move faster. Heating the molecules increases its kinetic energy, which does just that. And the faster the molecule moves, the sooner it collides with itself and its surrounding. Increasing the frequency of collision does the pressure. This is one of the reasons why if you cook food in an enclosed pot, the pressure increases, or how a hot air balloon stays inflated with fire. Just like most things in physics, we could explain it with mathematical equations, which allows us to prove, quantify, and make predictions. First, let's make sense of the relationship between pressure, volume, temperature, and also the number of particles, but in this case we're going to use the number of moles. And the number of mole is really just the number of particles over Avogadro's constant. We know from the first method explained that if the particle is a constant and the temperature is also a constant, when the volume decreases, that means the particles are being congested, the pressure would increase. And from that logic, we could also say that if the volume is a constant, the temperature is a constant, and when the number of particles increase, the pressure would increase. And also in the second method, we know that if the temperature were to increase with the number of particles and the volume as a constant, the pressure would increase as well. So from here, we could say that pressure is inversely proportional to volume. Pressure is proportional to number of particles, or number of mole in this case, and also pressure is proportional to temperature. Put them all together, you could say that pressure is proportional to the number of moles, the temperature, and it's inversely proportional to the volume. Now, but being in proportion isn't equal. In order to make it equal, we have to multiply by a constant. In this case, we're going to multiply by the gas constant, which is represented by R, and it's equal to about 8.31 joules per mole Kelvin. So now we could write our equation as pressure is equals to number of moles times the gas constant times temperature divided by volume. And this is the famous ideal gas law equation in thermodynamics. But we also know that pressure is affected by height or depth. And the deeper you go, let's say underwater, which is when the height is increased, the pressure would increase. Now to show this relationship, we could actually use the original formula, which is pressure equals to force divided by area. You see, weight is a type of force and is given as mass times gravity. And volume is really just area multiplied by height, or a kind of length. So therefore we could also say that area is equals to volume divided by height. If we were to substitute these two together into the original formula, you get pressure equals to mass times gravity divided by volume divided by height. We could rewrite this by pulling the h up and write mass times gravity times height divided by volume is equals to pressure. And we also know that density is actually mass divided by volume. And since we have mass divided by volume over here, we could replace that as density, so we will get density times gravity times height. So ultimately we have pressure equals to density times gravity times height. Because water has a much higher density than air, the deeper you go, the pressure would actually increase dramatically. This is one of the reasons why it's such a challenge to explore the deep sea, and it's one of the many mysteries of Earth. A vacuum is really just a way of expressing not having any molecules in a specific space. Some people might even call this some kind of suction, but make no mistakes, in physics, nothing sucks. And I mean it both ways. What's really happening is that the higher pressure, such as atmospheric pressure, pushes stuff towards the lower pressure region, and it might even crush this box. To prove this, because we know the atmospheric pressure, gravity, and the density of water, we can calculate that it only has enough pressure to push water up roughly 10 meters high. So if you create a vacuum at the top of a building, it will never draw water up higher than 10 meters. And indeed, this is true. Another interesting fact is that you might realize the water nearest to the vacuum starts to boil, simply because it takes very little energy for water to expand into gas in a vacuum. This means that pressure can actually change the boiling and freezing point of other matters. Here we have a poorly drawn aerodynamic wing. In general, there are two ways that allows the wing to generate lift. The first way is by directing the moving air downwards, which pushes it up according to Newton's law. So the wing needs to be at an angle, and we call this angle the angle of attack. The second is to make the air move faster at the top than the bottom. Now sadly, we're not going through in detail what Bernoulli's principle and its equation could teach us, but one of the things we know is that the faster moving fluid has lower pressure. And the wing's design causes air to flow more freely and faster at the top than the bottom. So there will be a pressure difference causing the higher pressure at the bottom to push the wing upwards, generating lift. In fact, when a fast, low pressure wind seemingly blow off the roof of a house, it actually first causes high pressure air in the house to explode outwards, pushing the roof from the inside out. In an enclosed system, fluid tends to have roughly the same pressure everywhere against the walls of the container. This is known as Pascal's Law. We can use this to do something quite interesting. Imagine a guy pushing against one of the walls containing the fluid. If he pushes with 100 newtons of force and the wall is about 1 meter square, the fluids at the other side of the wall will experience a pressure of 100 Pascal. But if the container had another movable wall at the other side that is 10 times wider in area, the force pushing out will be 1000 newtons. This is how we can use pressure as a force multiplier. Note that force isn't magically created. We are actually trading the extra distance traveled by the first wall to push the other. Lastly, let's talk about YouTube. No, not that YouTube. Like and subscribe, by the way. I mean this tube shaped like a U. Imagine two different liquids that will not mix poured into it from different openings. The heavier, denser liquid is likely to occupy the lower part of the tube, and you might get something that looks like this. You can draw a line where the fluid meets, and like a scale, we can say that the pressure of the fluid just above or at the line on the left is equal to the right. How's this useful? If you know the density of one of the fluid, let's say something common like water, you can then calculate the density of the other. Or we can even connect gas at the other side to measure its pressure. All this with some very simple apparatus and some basic understanding of the equation which we talked about. Pressure is literally all around us, and many tools and structures were built with this in mind. I hope today we have a better understanding of pressure and some of the benefits of having such knowledge. Hope to see you in the next video, don't miss it. It might take a bit longer to make because a lot is happening and I will be moving. But that's it for now, have a pleasant day, bye bye.